So what is 532 factorial equal to? Let's try the same thing. This is n. And look at the logarithm of n. So the logarithm of 532 factorial. This, of course, is the logarithm of 532 times 531 times 530, etc. So it is the logarithm of 532 plus the logarithm of 531 plus, etc. plus the logarithm of 1. Okay? We have to add lots of logarithms. Now, let's look at this way. But perhaps, you know what, I want one more. This is the logarithm of 2 plus the logarithm of 1. Okay? Now, let's visualize this. The logarithm of 1 just happens to be 0. And let's use the area of a rectangle as a visualization. The height of this rectangle is logarithm 1. The width is 1. Next rectangle has the same width, 1. So it has length or height logarithm 2. The next rectangle, again width 1, height logarithm 3, etc. And we can keep visualizing these numbers as area. Why? Just because I want to. Okay, there is no particular reason at the moment. And here we have logarithm of 531, again with 1, and then logarithm of 532. What we want to do is compute the sum of all of these. So we want to compute the sum of all these areas. This is very hard to do, but what we can do is we can make a guess, we can estimate, we can approximate them. Okay? To do this, we'll introduce coordinate axes like this. And label this 1, 2, 3, 4, 5. Okay, so 2 is where the logarithm 2 rectangle begins. So this is 531, this is 532, this is 533. As a matter of fact, this then is the logarithm of 2. If this rectangle has the height has area logarithm 2 and its width is 1, then this needs to be logarithm 2, as is this logarithm 3. So what we get is, if we connect all these dots, we get this situation here. You notice that this is of course the function f of x is logarithm in base 10 of x, and I think it has become pretty clear what we are going to do. We cannot really compute this sum, but we can approximate it by computing an integral. As a matter of fact, it is easier to compute this integral than to compute that sum. We will overestimate it, okay? I think you can see that we have these additional pieces here that we actually don't want. So what we get is something, we get an upper bound. What we need to compute, naturally read, is the integral from 2, we don't need to 1, 2, up to 533 of this logarithm in base 10 of x with respect to x. This integral is an upper bound for our sum. Okay, let's do that. First of all, logarithm in base 10 of x. can be rewritten as the ln of x over the ln of 10. This is another formula we used, we derived it once, to change the base of a logarithm, and you know that ln is more convenient in calculus. So we can rewrite this integral and say this is the ln of x divided by the ln of 10. ln of 10 is just a number, so this is 1 over ln 10 times the integral from 2 to 533 of ln x dx. And this is an approximation of log base 10 of n. Now if we try to evaluate this integral, then we find it's hard to find the antiderivative. We can use a trick here. 1 over ln 10 is the integral from 2 to 533 of 1 times ln x, and now we use integration by parts. This is 1 over ln 10. Well, this is u dash and this is v. We get this is x times ln x minus the integral of u times v dash. So x times the derivative of ln x is 1 over x dx. Now this is 1. So the whole integral is just x. Let me replace this. This is x. And we need to evaluate this from 2 to 533. What we get is something a bit nasty. It's still equal to 1 over ln 10 times, let's actually rewrite this as 1 over ln 10, forgive me, and take out x. It's a bit easier to evaluate. Okay, and now I'll put in the limits. So it is 533 times ln 533 minus 1 minus 2 times the ln of 2 minus 1. We could simplify slightly, but not considerably. If we type this in, unfortunately I have forgotten to do that. Give me a second, please. Minus 1 minus 2 times the ln of 2 minus 1, and all of this divided by ln 10. What I get is approximately 1222.13. Well, this is a very rough estimate, so let's focus on the integer part. We know that the logarithm in base 10 of n is approximately 1222, and the n therefore is approximately 10 to the power of 1222. That's the approximate number of arrangements there are. Okay, and perhaps just to tell you the exact number, well, the exact number is a lot of digits, but a better estimate would be 7.9, actually 7.99 times 10 to the power of 1220. Okay, so we're off by approximately a factor 12, but well, in numbers with such many digits, that's actually forgivable. I'd say we have gotten quite close by computing an integral instead of a sum. Isn't that nice? That's how you can at least approximate a factorial using integration.